All right, this video is on intramolecular forces and intermolecular forces. So the sheet I've given you here is intra versus inter. We're going to be focused mostly on intermolecular forces, not intra. So on intramolecular forces, your bonds that are holding elements together, which are really strong. So if we have like a water molecule there, your intramolecular forces would be your covalent bonds holding the oxygens and the hydrogen. So to break those apart takes a chemical reaction and is tough to do. So those are strongly held together. So ionic bonds, polar, covalent, nonpolar, those are intramolecular forces. Intermolecular forces, or what we call IMFs, are what we're going to be concerned about. So intermolecular forces would be this molecule and another molecule of the same kind or a different kind next to it. So there are forces between those two molecules that are called intermolecular forces. So this molecule is a little bit attracted to this molecule. It's all based on positives and negatives attracting, positives and negatives. So if you think about a water molecule has got a pretty negative end right here, and the hydrogen's a pretty positive end. So this positive hydrogen is attracted to this negative oxygen. Okay, so there's some attraction there. That is an intermolecular force. So the more tightly held these molecules are together, the more likely they are to be a solid at room temperature. They have higher melting points, higher boiling points, lower vapor pressures, things like that. So these forces holding them together, and these forces are not near as strong as the forces in those bonds. Much easier to make the molecules spread apart than it is to break apart the hydrogen and the oxygen. So there are 4 or 5 major intermolecular forces. And again, it's always force of attraction between molecules. So first thing that's in all molecules are called London dispersion forces, or LDFs. So a lot of times we just write these as LDFs, London dispersion forces. All molecules have those. Every single molecule has these. Polar, nonpolar, every molecule has London dispersion forces. Nonpolar molecules, it's the only force of attraction between two nonpolar molecules. And dispersion forces are kind of like this. If we have, for example, fluorine, F2, you've got some electrons floating around the outside. Okay, each fluorine, total electrons, each fluorine's got 9 of them. So it's got all those positives and negatives floating, all those negatives floating around. Well, normally they're evenly distributed. So in this case, there's really no charge on this F2 molecule. But those electrons have the ability to shift to one side or the other, and that's called dispersion forces, where you can kind of make this into a polar molecule for a short time. So if these electrons, if something positive would come close to this, those electrons would shift to this side. So a bunch of these electrons would now shift over here. And now this side's very negative, and this side's kind of positive. So more electrons, or a lot of times they just say more molar mass, means more dispersion forces. So bigger molecules with more electrons can become polarizable. In other words, they can become slightly polar for a short period of time. So two nonpolar molecules are attracted to each other by something called dispersion forces. And dispersion forces can be strong, but they are generally the weakest force of attraction. So these go from weaker to stronger for the most part, I guess, except for the very bottom one maybe. Next one, dipole-dipole, just means you have a polar molecule and a polar molecule. So if we have like, actually I'm going to change that. We have that molecule. It's a very polar molecule. It's got a very positive end and a very negative end. Lots of electrons on one side, not very many on the other. So if we have another one of those molecules, they would orientate themselves like this, where this positive end is attracted to this negative end. So there's pretty strong attraction between that and pretty strong attraction here because there's negative and positive. So dipole-dipole forces. This is a dipole. It's got 2 poles. This is a dipole. It's got 2 poles, a positive and negative pole. Dipole-dipole just means the positives and negatives attract between them. Stronger than dispersion forces typically. Okay, now dispersion forces can be stronger than this, but in general, dipole-dipole is stronger than dispersion. Hydrogen bonding is also dipole-dipole, but it happens when hydrogen is connected to NOF. So this would not be hydrogen bonding. Okay, and it should not be called hydrogen bonding. It should just be called hydrogen attraction, but this would not be hydrogen bonding because it is not hydrogen connected to NOF. So water would have hydrogen bonding in it. So if we have a water molecule, this is not hydrogen bonding right here. Those are hydrogen. That's a hydrogen bonding to an oxygen. Hydrogen bonding would be it should just be called hydrogen attraction. Hydrogen bonding would be this hydrogen off this molecule attracted to this oxygen on this molecule. So it's a pretty strong special force of dipole-dipole where there is pretty strong attraction between this hydrogen and this oxygen. Okay. So that is hydrogen bonding. Here's the thing though. The hydrogen involved in hydrogen bonding, this hydrogen that's involved in hydrogen bonding, has to be bonded to nitrogen, oxygen, or fluorine and attracted to nitrogen, oxygen, or fluorine. So this hydrogen has to be bonded to NOF and attracted to NOF. So if we had like this molecule and an oxygen off of water over here, there would be no hydrogen bonding between this hydrogen and this oxygen. The hydrogen involved has to be connected to nitrogen, oxygen, or fluorine and attracted to nitrogen, oxygen, or fluorine. So that makes this hydrogen very positive when it's attracted to nitrogen, oxygen, or fluorine because they're so electronegative. Okay, so hydrogen bonding is in that example. Ion dipole forces would be like if you dissolve a salt in water. So ion dipole would be like a salt in water. So for example here, when you put like sodium chloride in water, so the sodium splits apart into, you get sodium ions, you get chloride ions. So that's an ion. Water is a dipole. So if we think about drawing a water molecule close to this, well, the oxygen end, which is a little bit negative, would be attracted to this positive ion. So ion dipole. Remember, it's called a dipole because it's got two poles. It's got a negative and a positive end. So ion dipole. If you had water over here, it'd be the opposite way. The hydrogens would be here. So ion dipole forces, pretty strong forces of attraction. Last one here, dipole-induced dipole. Dipole-induced dipole. So let's say we have a dipole such as a water molecule and a nonpolar molecule like CCl4. Well, this has no charge to it. There's not a positive, it's not a dipole, not a positive negative end. But if it comes close, if a dipole comes close to it, so something with a charge on it, like this has a pretty negative end here, the electrons in this can shift to one side and induce this into a dipole for a short period of time, just be a temporary dipole. So these negative electrons might shift some of these electrons over to that side and make this have kind of a partial negative and partial positive. So that's a dipole inducing this into a dipole. Or I think if I brought like a sodium ion close to this, now those electrons would be shifted to this side and that molecule would turn into a temporary dipole. Factors that are affected by intermolecular forces, boiling points. So stronger forces, higher boiling points. Molecules don't want to spread out, okay, into a gas. Again, all of these are increased with stronger intermolecular forces. We'll get into those. Pause for a second. All right, last part of this. Here's a quick little review over this stuff. So first thing, again, here's a water molecule. The bond holding the oxygen and hydrogen is an intramolecular force, a force within the molecule, very strong. Intermolecular force would be this molecule attracted to this molecule. And the intermolecular forces between two water molecules would be, first of all, London dispersion forces. So every molecule, there's always London dispersion forces between two molecules because they have some electrons. Oh, those are the weakest forces. This would be dipole-dipole because water is a dipole. It's got a positive and negative pole, positive negative pole. And it would be hydrogen bonding because you have hydrogen connected to nitrogen, oxygen, fluorine, and attracted to nitrogen, oxygen, fluorine. Hydrogen bonding is the strongest intermolecular force in water molecules or between two water molecules. explains why water has a pretty high boiling point. It's hard to make the molecules spread apart. It takes a lot of heat to make that happen. Hydrogen chloride. There'd always be dispersion forces between these two molecules. There'd also be some dipole forces. You want to get in the video? You want to get in the video? Here's an example of a dispersion forces. This is just an individual atom, like maybe it's just a lithium atom or something like that. It's got 3 electrons. So normally these electrons are evenly distributed. So it'd be a very non-polar atom. But something can come along and make those electrons shift to one side temporarily. So then it becomes a temporary dipole. In other words, there's a negative and a positive pole now. So now it's got some dipole characteristics. I don't know if we scroll down here. Not sure what's going on. All right, here's a DNA molecule. So if we look at, here's a molecule, here's another molecule, actually a guanine and a cytosine. Notice you've got a hydrogen here connected to NOF, nitrogen oxygen fluorine, and attracted to nitrogen oxygen fluorine on this side. So that would be hydrogen bonding here between these two molecules. So there's hydrogen bonding, which holds those two molecules together very, very strongly. ICL, whenever you have 2 different elements, there's probably always a stronger attraction for electrons between one of them. So this molecule is a little bit polar, but not super polar compared to like an HF or an HI or an HCl. There's a big difference in them. So it still would be a dipole and a dipole. So it'd be dipole forces between those 2 molecules. We're looking at that. Here's dipole-induced dipole. So here's a dipole molecule like water or like HCl. So it's a dipole because it's got positive negative pole. This would normally be something that has an even distribution, but here is the dipole inducing this into a dipole. This positive charge is pulling electrons this way, shifting the positives that way. Now this thing is shifted into an induced dipole, where normally it probably would be evenly distributed. Here's an ion, like a lithium ion or a sodium ion or potassium ion, inducing this into a dipole. Forces between these. So again, there would always be dispersion forces, and more electrons is more dispersion forces. But this molecule, this is a dipole. It's got a positive and negative pole. This is a dipole. It's got a positive and negative pole. So there is dipole forces. The negative on this is attracted to the positive on this. This just means partial positive charge, partial negative charge. There would not be hydrogen bonding here because the hydrogen is not connected to NOF or attracted to NOF. It's a sulfur atom involved in it. So all that means is there's not quite as much attraction as there would be if this was a nitrogen oxygen or fluorine, and this was a nitrogen oxygen or fluorine. There'd be a little bit more attraction, so a little bit stronger. All right.